So I wanted to continue on where we left off last time about Moore's circle of strain, and we got to Moore's circle of strain essentially by using Hooke's law for Moore's circle of stress. So with that, I'm going to start this problem, and I'm going to do it a couple different ways. So I'm going to start by saying that I am given that the strain epsilon x is equal to 520 times 10 to the minus 6, that epsilon y is equal to minus 80 times 10 to the minus 6, and that gamma xy is equal to 280 times 10 to the minus 6. And we'll also take that Young's modulus is equal to 30 times 10 to the 6, so that'd be PSI, looks like something like steel. We're in English units, and Poisson's ratio is 0.3. And what I'd like to find then with this, I would like to find the principal stresses. So we have something that's now more complicated than just taking a state of strain and drawing Moore's circle of strain and finding the principal strains. We have a situation of given strain. This is a plain strain like we might have with a strain gauge. This comes up all the time in practice or industry, where we have strain measurements because they're easy to arrive at, they're easy and cost effective to make, but we would really like to get to stresses. Okay, so that's going to be our test. And we're going to do this two ways. We're going to try it first by finding the principal strains with Moore's circle of strain and then using Hooke's law, because if we have principal strain, we know when we transfer those with Hooke's law, we will have principal stresses. And then we'll try it a second way, where we just take this given information, we transfer it with Hooke's law immediately into stress, and then we'll use Moore's circle of stress. So hopefully our answers will be the same on this as we go through this. So for this first method, we're going to do Moore's circle of strain. And then for Moore's circle of strain, we're going to use Hooke's law. And then we'll do it a second time, and we'll do it exactly the opposite of that. The one thing that I will tell you in evaluating these two situations is this also works for 3D. Okay? This order of doing this works for a 3D problem, whereas the other one, the next one that I do, will not work for a 3D problem. So this first method may have an advantage in that regard. So let me draw Moore's circle, and my circle is going to be predominantly positive as I think about where I want to put this on the paper. So we'll have epsilon here, epsilon times, we'll say 10 to the minus 6, and then this axis here is gamma divided by 2 times 10 to the minus 6. And again, if you're following along with your author, you will be taking the axes pointing down, and you'll rotate things differently. You'll get the same answer, but you don't want to mix and match our two methods. So if I look at what's going on in the x, we have what, 520? Is that right? There's 1, 2, 3, 4, 5, so a little past 520. So I'll be somewhere right there. And then this 280, so that gives me what? 140. If I take 280 and I divide it by 2, that gives me 140. And this gamma xy, this is a positive number, right? So if I were to look at that element and I have a positive strain, that would look like that, wouldn't it? So I would then have the shear stresses like this, and the x face and the y face. So is x going to be positive or negative? X is going to be negative, isn't it? If you look at just that x right there, it tends to rotate it counterclockwise, so that would be plotted negative. So I'd be down here at minus 140. So I have then 520. So I'll put x here at 520 and minus 140. That's the x point right there. Now if I do y is minus 80, so I need to go to minus 80, I'll be about right there, and we would recognize that we probably would be positive. Does that work over here in the y direction? Yeah, the y direction is going to tend to rotate that, looking at just the y. If we look at just the y piece, that's going to tend to rotate it clockwise, isn't it? So with that, I could say that I have y that is minus 80 and 140. And of course, that's times 10 to the minus 6. So there's the diameter. Like that. And I brought the pencil compass in. We'll see if we can do some justice with that. Should be centered up there. Well, that's close. Okay. So that's our circle. And the principles hang out right here. We could talk about this point being epsilon 2, and maybe this one being epsilon 1. We usually just label those going from left to right. So if I talk about the center point then, that's going to be what? 520. Just the average of those, 520. Plus a minus 80 divided by 2, which gives me what? 220, is that right? Yeah. 220, and that's 220 times 10 to the minus 6. I need to remember that. Then the radius, if I look at a let's say this triangle right there. I'm running out of pen. So we said that this was what, 140, and this is going from the center point, which is 220, to this point here, which was 520. So that's what, 300? So I've got that the radius is going to be the square root of 300 squared plus 140 squared. It should turn out to, I think, 331, of course, times 10 to the minus 6. Let me double check that. Yeah, good. So I could talk then about epsilon 1 being equal to the center minus the radius. So I'll have 220 minus 331, which gives me an answer of minus 111, of course, times 10 to the minus 6. And then epsilon 2 would be equal to the center plus the radius, which is 220 now plus 331, which gives me 551, positive 551 times 10 to the minus 6. Does that make sense from our picture? We know we should be something greater than 520, which 551 is, and we should be something less than minus 80, which minus 111 is. So that seems to make sense. So we pulled epsilon 1 and epsilon 2 off of there, essentially the principal orientation. Is there questions with that? So now what I'd like to do is, using that epsilon 1 and epsilon 2, I'd like to go to Hooke's law. So we've done Moore's circle of strain. Now we're going to go to Hooke's law. And for sigma x, I know that that's equal to Young's modulus divided by 1 minus Poisson's ratio squared times epsilon x plus Poisson's ratio times epsilon y. And likewise, sigma y is equal to Young's modulus divided by 1 minus Poisson's ratio squared times the quantity epsilon y plus Poisson's ratio times epsilon x. So I have to figure out what I'm going to call epsilon y and epsilon x. Well, let's see. I usually just take the closest that we rotate it to. So we could say that this epsilon 1 is our epsilon y. And we could say that this epsilon 2 is our epsilon x if we were to rotate that diameter up there. So with that, then, I have that sigma x is going to be equal to 30 times 10 to the 6th divided by 0.91. 0.91. So that'll come up again, so I just did that all at once. And then epsilon x, that was the larger one, 551 times 10 to the minus 6 plus 0.3 times minus 111 times 10 to the minus 6. And when you get done with that, that turns out to be 17,067 psi. And I've got too many significant figures there, but so you can check it with your own work. I'll just go ahead and leave those. I mean, we just call it 17,000 psi. Then we do similar work for sigma y. That's going to be 30 times 10 to the 6th divided by, again, 0.91. And now I'm going to have the minus 111 times 10 to the minus 6 plus then that 0.3 Poisson's ratio times 551 times 10 to the minus 6. And that gives us 1790. Yeah. So those are our two values. So I got sigma x at 17,000. I got sigma y at about 1,800 psi. And those are actually principal. Those came from the principal strains, so those would be principal. When I rotated this to this principal orientation and then use Hooke's law, if I'm a principal strain, I will get principal stress. So this is the answer. These are principal. Okay? Questions of that? So that was Moore's circle going to Hooke's law. And the probably the thing to remember is this works on 3D. So if you have a 3D problem with your Z strain either being principal or zero, you can do it with this. Now I'm going to reverse this order and I'm going to do Hooke's law and then Moore's circle. And the important point there is that doesn't work on a 3D problem. So we'll go to page 3. So now try Hooke's law, then Moore's circle. And that's going to be Moore's circle of what? Stress, isn't it? So while this one we used Moore's circle of strain, in this last one and went to Hooke's law, we're going to do Hooke's law and then we're going to use Moore's circle of stress. And this doesn't work on 3D. So that's something to keep in mind. I don't know that one method is particularly any more difficult or demanding than the other method. So if you're going to remember one, probably the first one is the better one because that will work on 3D problems. So if I repeat the given information here, we've got epsilon x is equal to 520 times 10 to the minus 6. Epsilon y is equal to minus 80 times 10 to the minus 6. And gamma xy is equal to 280 times 10 to the minus 6, and of course have a Poisson's ratio and E. I won't repeat those, we probably remember those. But if I use Hooke's law, I'm going to find out sigma x. And we know that sigma x is equal to Young's modulus divided by 1 minus Poisson's ratio squared times epsilon x plus Poisson's ratio times epsilon y. We just used that one, didn't we? So that looks like in this one that we're going to have 30 times 10 to the 6th divided by 0.91 again. And now epsilon x, that's 520, times 10 to the minus 6 plus 0.3 times minus 80 times 10 to the minus 6, which gives me a value then for sigma x, the strain in the x direction, as 16,352. Again, too many significant figures, but so you can check your work with this. Okay, that's not principal. Okay? That's not principal, but we'll be able to enter more circle of stress with that. So now I've got sigma y. Hopefully, did I call this sigma? Hopefully not epsilon. That's sigma. So sigma y is Young's modulus E divided by 1 minus Poisson's ratio squared times epsilon y plus Poisson's ratio times epsilon x. So going through that, we have again 30 times 10 to the 6th over 0.91. And now I'm going to have minus 80 times 10 to the minus 6 plus 0.3 times 520 times 10 to the minus 6. And that gives us then sigma y being equal to 2,505. Again, too many significant figures, but so you can double check that. We've got that. Now, since this is not principal, I need to deal with the shear, right? I know that tau xy would be equal to the shear modulus of elasticity G times the shear strain gamma. We'll call that gamma xy. So I could say that this was Young's modulus divided by 2 times 1 plus Poisson's ratio. Remember, that's what G was. And then we'll multiply this by gamma xy. Do we have gamma xy? Yeah, we do, right there. Okay, so this is 30 times 10 to the minus 6 divided by 2 times what? 1.3 times gamma xy is 280 times 10 to the minus 6, which gives me 3,231 psi, and that is tau xy, our shear strain. Yes? Oh yeah, this should be 30. Did I make that mistake anywhere else? No. Thank you. That would be positive. Other questions? So now, if someone came along and told you, well, sigma x and sigma y and tau xy, could you draw more circle of stress? I suspect so. So let's do that. So now to Moore's circle of stress. So we've got from the and I'm just going to summarize what we had here on this other sheet: sigma x, sigma y, and tau xy. So sigma x is equal to 16,352. Sigma y is 2505, and tau xy is 3231, and those are all psi. So let me draw more circle of stress. If you're running out of space, it's predominantly positive or completely positive. So we've got our tau and we've got our sigma. Those will be in psi. And let's see, let's do x. So x is positive. I'm going to be out here at, yep, that looks like about 16,352. Okay, there's 16,352. I mean, the other thing is I start counting here. 1, 2, 3. Oh, I lost count. 1, 2, 3. And I always wondered how many days I could come in here and do that before you go to the dean of students and try and have me committed. But anyway, so let's not go down that road. We've got 16,352 right there. And then this tau xy, what does that mean? Sometimes this is a little trouble. put that onto the element, I mean, as far as that goes, we had 16,352 there. This one was positive, so I have 2,505 there. And then on the x face in the y direction, x face in the y direction, so we can fill the others in, can't we? And this becomes then 3231. So now when I talk about this x face, it's going to tend to rotate it which way? Counterclockwise. So we know it's down here, and right there, there's 3231, and there is x. That represents the point 16,352 and minus 3231. And the way I got minus 3231 is I went, this is the shear stress on the x face. There's the x face in the y direction, so I drew that arrow like that. That dictated where all my other arrows went. And I'm kind of recapping this because this will be our last problem with more circle of stress or more circle of strain. So now when you look at this element, you think about which way does the x tend to rotate. If we ignore these others and we just look at that, that would tend to rotate this counterclockwise. So I plot that negative, right? Okay. And then what if we have this one here? Up here, the y. What's the y going to do? When I look at that one, it's going to rotate it clockwise. So we'd expect x to be plotted negative, it is, and y should be positive, which it is. So here's a point here that will represent y. That's going to be 2505 and positive 3231. So there's the y point. The biggest problem, if we were to give a quiz on more circle of stress or more circle of strain, the biggest problem is people get the diameter wrong. If this is the right answer, a lot of people would end up with the diameter the other way. So really concentrate on that as you're going through the homework problems. Well, I can then draw this diameter and use the pencil compass one last time. There we go. Okay. So there's more circle, and I know that if I rotate this, that if I take this x point and I can rotate it up there, this, maybe we'll call that sigma 2, our principal stress, and I take this y point here and I rotate that down to there, I'm going to have sigma 1, right? So let's figure that out. What's the center on this thing? The center is going to be equal to 2505 plus 16,352 divided by 2, which gives me 9,428.5. Okay. Again, too many significant figures, but since I'm going to compare this to the previous example, I'd like to try and avoid a little bit of round off. Presumably probably keeping that in your calculator anyway. So now if we look at, let's say this triangle right there, we have this side that's 3,231. We have this one going from 9,428.5 to 16,352. So we could say that R is equal to the square root of 16,352 minus 9,428.5 squared plus 3231 squared. And that turns out to be equal to 7,640. Okay. So with that, I could then say that sigma 1 is going to be the center minus the radius, which would be 9,428.5 minus 7640, which turns out to be equal to, I think 1789, isn't it? If I ignore that, I guess I'd have to round that 0.5 to 29, wouldn't I? Yeah. So we're within a half. Okay. And sigma 2 would be equal to the center plus the radius. So 9428.5 plus 7640, which gives me an answer of 17,068. So here we had to add a add 0.5. Here we subtracted the 0.5 in terms of rounding that off. So even if you wouldn't have done that, you would have come very close to this value, and our only difference would have been round off. So two good methods. This method won't work on a 3D problem, so I would probably, if you're going to just look at one method, I would look at using Moore's circle of strain and then using Hooke's law, although if it's a 2D problem, you can do it the other way. You can use Hooke's law, and then you can do Moore's circle of stress. Questions of that? So going through a problem like that hopefully gives us a lot of practice with Moore's circle of stress, gives us a lot of practice with Moore's circle of strain, also using Hooke's law. So you've got quite a few homework problems that deal with that, so make sure that you're working on those. Well, the next section, we've got a short section, and it's really nothing new, except we're going to kind of repackage some of the things that we've talked about. And that's to talk about combined stresses. Okay, so we're going to take what we've done in the past and kind of put it together and maybe look at it with a slightly different perspective. It's, like I said, it's a fairly short section, and that will then lead us into one of two last sections that are more involved. Deflection and beams will be where we'll spend most of the rest of our time this term, and then we'll finish up with a short section on column buckling. Column buckling is not a small subject, but we're just going to kind of start that. Civils and mechanicals are probably going to treat that quite a bit differently, so we'll just start that conversation as we wrap up the term. But thinking about combinational stress, you may have thought, well, you really sanitized your examples in here to turn in something into a purely axial problem or a purely torsional problem. You know, in my life, things are a lot more complicated than that. So we want to start to look at some of those things. Maybe we have something, some sort of a structure or a bracket or something, and it has something like this, and we apply some load to it. We'll call that load P, and it's out there some distance D. And we could really say, I mean, if we were to go look at a section through there, what would we have? We'd, at that section, we would have compressive force. Is that true? Yeah. And then we would also have a bending moment on that thing that's equal to the value of P times the distance D, right? Whereas that compressive force is just P. And this would really be equal to, if we were to think about it, the example of compression. So when we get compression, we could look at just this compressive force and add it to the example of bending. P times D. If I add those two up, we have the situation, don't we? And this is probably a good way to think about this, because if I look at this, I can say, well, for the axial load, what do we have? We'd have some axial stress, wouldn't we? So let me represent that axial stress like this. And for the bending, what are we going to have? Well, it's probably going to have compression on this side and tension on that side, right? So let me represent that. So if we have tension here, like that, and then we have compression here, like that. And we can say that these stresses, this sigma, would be equal to P over A, whereas this sigma here is going to be equal to what? Minus My over I, our bending stresses. So when I put this together, what do I have? When I sum these up, using this space over here, it looks, draw it a little larger so we can see it a little easier. Let's see, if I start to add the compression to the tension, that's going to reduce the tension, isn't it? So maybe I've got something that looks like this. And then what happens? I add the compression to the compression, and we have tension here, we have compression there. Well, those are going to get much larger, aren't they? So something like that. And effectively, you'll see that this neutral axis here actually shifted. We shifted the neutral axis. And we can talk about then the stress here, sigma, being equal to, and maybe we should say minus P over A because it's compressive. So minus P over A plus or minus then My over I, right? Wouldn't the right side of the big one? Oh yeah, I've drawn this in the wrong way, haven't I? Let's see, this is, I've got tension and compression, so I should have a small amount of tension. And these need to go the other way because I got a lot of compression. Yeah. Is that what you're asking? My arrows are the wrong way? Yeah. Now I think we're okay. Yeah. And effectively I have shifted this neutral axis, then I've actually moved the neutral axis. And this is something that comes up quite a bit. Let me look at an example. You go downtown and really any town, certainly downtown Salem, and you look at the way buildings might be constructed. And they might have some concrete block buildings. We call them CMU, concrete masonry units. So we've got these blocks that are stacked up. This is on a foundation here. Then someone has come in and poured a floor. And maybe they put a ledger on this. They've got the roof structure in here, and maybe they've got a parapet then. They tend to put those parapets on for fire safety. So they either have a floor, a roof, and a very, very common arrangement. And let's say that we have some load on this from this direction. So this could either be wind or seismic. So you got wind or earthquake there. And maybe that's trying to deform the wall this way, right? So we're going to end up in this wall with tension on this side and compression on that side. So we go downtown, we look at a masonry wall that stood there faithfully for 70 years. Masonry wall that's 70 years old. Does it handle compression well? Yeah, pretty well. Okay, masonry handles compression pretty well. How about tension? Yeah, not so good on the tension, right? Okay, so you end up with a lot of tension stresses here that you don't want. And a lot of these masonry structures are hollow. So sometimes what they'll do is maybe you'd go in here and you'd drop a piece of rebar in and fill it up. And that would be one way to do a little seismic retrofit on this. Another way is simply what they call grouting the cells. The cells were probably, a lot of the cells were probably left void or empty because that gives you some better insulation properties. But if you start to fill these up, if you grout them full, so you fill those blocks full, and even if they put some rebar in it in the past, they may have only done every other cell or something like that. If it's a prison, then they do all the cells. It's fairly easy to knock a hole in one if it's not grouted. So we fill those all up. What has that effectively done? We make the wall heavier, right? We add weight to this thing. You might say, well, my goodness, we're talking about an earthquake. The worst thing we could do is add weight. But really? When we add weight to it, what happens to the tension? Well, in this example here, what happened to our tension is we added weight. It got smaller, didn't it? Yeah, if you increase this p-value, if you increase that value there, that tension will get yet smaller, won't it? So as we add weight to this, which seems kind of unintuitive, we actually reduce this tension. Now the compression is going to go way up, okay? The compression is going to go way up, but you'll be able to reduce the tension maybe to something that you can manage. Okay? Maybe you won't be able to manage it, but maybe you can. But that's one strategy, is you grout those full. If you can put some rebar in there, all the better. We don't want to turn this into a structural retrofitting class, but if that doesn't work for you, what you may end up doing is increasing the size of this footing here, and then you come in and you frame a wood or a steel wall in here. Okay, and then you attach the masonry to that wall. So basically you turn what's been your structural masonry into a masonry veneer, and you have the wall supporting that. Okay, and then the parapet is really a death wish. So if you look at after they've had an earthquake or something, and there's rubble on the ground, and you went, well, where did it come from? Well, it's probably the parapet that fell off. So that's always falling off on people or cars. So if you want to do structural retrofit, you're going to come up here and probably put some bracing to that parapet. Okay, because this parapet up there shaking around at the top of the building is a real problem. But this is a great example, a practical example, where we might add weight to something and you think that it's not going to help you, and it actually does. It reduces your tension stresses in that masonry. Now, it might not reduce them enough. That might not be a solution, but sometimes it can be a solution. You actually probably do this more than you think. Have you ever tried to cut a banana in two without a knife? No. Just me. Yeah. So, okay. If you ever have, little brothers or sisters or something, they're fighting over a banana, it's like, oh, tear it in half, you both get half, go away. So, yeah, okay, so if you just grab the banana and hork on it, you're just going to have a banana mess. Okay, no one's going to like that. But what do you have to do? You actually grab the banana, you put a little stress concentration in your fingernail, that's a whole other subject. But when you grab the banana, you're going to try and break the banana in two. What do? You pull on it a little bit. And what's that do? Reduces your compressive stresses from the bending, right? And just increases the tension stresses. So some of you, maybe your mother, is an expert at this already, if they can tear a banana in half. So. Anyway, that gets us to a pretty nice stopping point. We'll finish that subject up next time and get into beam deflections. Take care till then.